kind of area. So what I'll do is I'll start at a fairly elementary level, okay? But we won't end there. Okay, I'll tell you now. So we'll start with complex numbers. So I'm a mathematician. I work with complex numbers. I work in an area called complex analysis, which is the study of, I guess, calculus with complex numbers. So complex numbers are these kinds of things. They're an extension of the real numbers. Real numbers are not enough to do most things in math. So, the natural thing to do is extend them to include things like square roots of negative numbers and other things like that. But in general terms, complex numbers are more useful than real numbers because they allow you to solve things that you couldn't previously solve. But they look like this. The general form is x plus iy. X and y are real numbers. And I is the square root of -1, annoyingly called the imaginary number, although it's not imaginary. You can see it, it's right now. Geometrically, complex numbers are more interesting, okay, because unlike real numbers where you've just got the real line, complex numbers, because they're an extension to another dimension, the second dimension, and we usually use the Argand diagram here just to plot points. Okay, so x plus iy is plotted there. It is, you can think of it as a position vector to that point, or just the vector to that point, or just the point itself. So there's this dichotomy between the analytic part of complex numbers, but also the geometric part. And this goes on towards when you start looking at functions of complex numbers. Functions of complex numbers, you can think of them in two different ways as their definition. So things like z squared and stuff like that would be a function. But really, the way it's best to think about complex functions is as mappings from the complex plane, one complex plane to another complex plane. And we usually call these the z plane and the w plane. So here we've got w is equal to f of z, and you've got to think of that as mapping some set from one domain into another set. Okay, here we've got d1 mapping to d2. Okay, so it's a much more geometric area, okay, and it's very different to the real numbers. Okay, if you think about calculus, for example, there are lots of differences between complex functions and real functions. Okay, complex function. If a complex function is differentiable in an open set, okay, so an open set is a set without boundaries. If it's differentiable in an open set, then the derivative is also differentiable, and so on and so on and so on. Okay, so there's none of this rubbish about being able to differentiate once or twice or 3 times and then not being able to differentiate. The differentiable functions in complex analysis, complex numbers can always be differentiated. Okay. We call these functions holomorphic functions. You might see them called analytic functions as well, but I've recently started only using the word holomorphic.
They have to be continuously differentiable.
They do have to be continuously differentiable. There are bits that I might miss over occasionally in these slides, but they do have to be continuously differentiable. But what goes with it is the open set. The open set is part of the definition. Okay, yeah.
Differentiation is like it's the same. I mean, it's
defined
the usual way.
Yeah. Yeah. Except that you're talking about the limits in terms of the complex.
And how does this? How does it translate to the fact that, and obviously, these complex functions include the real functions?
Sorry?
And obviously, complex functions include the real functions.
No, they don't. Not when you're talking about continuously differentiable.
Okay.
A function, you're talking about something that takes f of x plus iy to x.
Yes.
Wouldn't be differentiable, wouldn't be continuously differentiable in the complex plane.
Okay.
So for real value functions, this is called smooth functions.
Sorry?
So for real value functions, this is called smooth functions.
Yeah. Yeah. There's a slight difference because smooth normally means infinitely differentiable.
Mm-hmm.
but that's different from being real analytic.
Okay.
Yeah, so there's a slight difference, but you know that. Okay. Anyway, so this is what I'll be talking about a lot. Holomorphic functions are interesting, but in their own right, but we'll look at them as applications in a minute. I'll talk a lot about conformality, really, when he's looking at complex functions. A complex function like this, if it's differentiable, a holomorphic function, I should say, if the derivative is non-zero, then it's conformal there, meaning that if you map z to f of z, then any two arcs are mapped to similar arcs with making the same angle. So these two arcs, although they're in different places and pointing in different directions, the angle between them is the same. Okay, conformal mappings come up a lot in applied maths. We'll talk a little bit about them.
How do you define this angle formally?
Well, you do have to be a little bit careful.
Yeah.
So you have to look at smooth arcs and things like that. But the derivative, as long as you've got a smooth arc, then the idea is that eventually the angle becomes the same. Okay. If a function is conformal everywhere, it is called a conformal mapping. So if it has no non-zero derivative, then it's called a conformal mapping. Conformal mappings are extremely useful. Okay, extremely useful. This is an example of one of this function z plus 1 over z maps this disk onto this aerofoil thing. It's called the Joukowsky transform. But they are weird. This function actually maps the inside of that disk into the outside of that aerofoil. Okay, so it is a bit weird. All sorts of strange stuff happens. This is nothing compared to the weirdness of conformal mappings. Okay, but they are really useful. Okay, but they are unique to the complex numbers, to complex analysis. Okay. I'll go straight to that second point. The famous Riemann mapping theorem says that any simply connected domain, okay, any simply connected domain that isn't complex plane or can be mapped onto any other simply connected domain by a conformal mapping.
And are these open sets or something?
Yeah. Always in complex, I always talk about, because holomorphicity is only defined on open sets, you only ever talk about open sets. That is the big flaw not the big flaw, that's the big downside of the Riemann mapping theorem, is that I remember when I first learned it, so this is great, it tells you what's happening on the interior, but it tells you nothing about what's happening on the boundary. Yeah, so there was about 70, 80, 100 years worth of research about what happens on the boundary. That will happen, you'll see that kind of coming up in the talk as well. So the Riemann mapping theorem says essentially that any two simply connected domains are the same, they're the same thing. Okay? And this is unique to complex numbers. In Rn, there are no conformal mappings. Okay? Although there's no interest in conformal mappings, would be a better way of saying it. Obviously, the identity is a conformal mapping and for things like that. But there's nothing like this in R3 and above. One thing to note is that for simply connected domains, conformal mapping is what conformal mapping is one-to-one. Okay, so also called a univalent mapping. Okay, and again, that only works in simply connected domains. Okay, so for simply connected domains, the boundary is, and that means the boundary is in one piece. Okay, the boundary is in one piece. Then the conformal mapping and the univalent mapping are the same thing. We're going to talk a lot about multiply connected domains in this talk. Okay, so in that case, lots of weirdness happens. But I'll give you an example of an application of this and kind of the ways this is used, because it will lead to where we're going. So this is this heat equation, the solution of the heat equation. Heat equation models the dispersion of heat along in a certain object. Okay, so over time, you see what happens is the thing kind of flattens out. Okay, the thing flattens out and disperses. Oh, excuse me. So in the long term, in the long run, excuse me, in the long run, the solution of the heat equation, the solution of the heat equation becomes stable. Okay, it spreads out all the heat, kind of displaces, and it smooths out, and it becomes stable. This is one of the central ideas behind behind the Ricci flow, which was used to prove the Riemann hypothesis. Not the Riemann hypothesis, not the Riemann hypothesis.
So you mean uniform, I guess?
Yeah, stable. Stable isn't the correct technical word, but the idea is that eventually, as t tends to infinity, this becomes a stable. It tends to a stable state essentially. And this solution is called a harmonic function. Is an example of a harmonic function. And the importance of this is that harmonic functions are invariant under conformal mappings. Okay, so meaning that if u is harmonic, then u of phi is harmonic. Okay, so so the heat equation, solving the heat equation in the rectangle is the same as solving it in any other shape. Okay, because conformal mappings can be used. This is not unique to the heat equation, it happens elsewhere. Happens with potentials. The Laplacian is actually the equation of the harmonic function, but it happens in fluid equations. That aerofoil is very important, that shape in the air is very important in fluid flow to help understand the airflow over that aerofoil. But it's also used elsewhere. Brownian motion displays some conformal invariance as well. Okay, meaning that probabilities associated with Brownian motion remain the same. And again, this is great because you have all sorts of conformal mappings, so you can always map something horrible into something nice. Okay. Right. Now, I'd like to not talk about harmonic functions, so I'll talk a little bit about, go back to talking about holomorphic functions and the link between the two. Holomorphic functions have obviously two parts, the real part and the imaginary part. Harmonic functions come up as they're always the real part of a holomorphic function. So you can extend harmonic functions to the complex plane. Okay, to the complex plane. And in quite a nice way. It's also, this kind of extension often has the same kind of growth conditions, so LP growth conditions on harmonic functions. If you know what they are, they correspond to similar conditions for the equivalent holomorphic function. So you kind of get this link between the two. Okay, so what is it, 20 past, and I'm going to define what a composition operator is at last. So this is kind of the history of what we're doing. This is the reason why this is interesting. This understanding of the composition process is important. Okay, it's knowing that a harmonic function composed with a conformal mapping is also a harmonic function is fine, but what can you then say about that new harmonic function? What can you say about what's going on? That's obviously very important when you actually want to do this kind of thing. Okay. Right. So we define this thing, the composition operator, C phi. Okay. C phi is a linear operator, maps f, a function f, to the function f of phi. So you think of that as a function itself, mapping a set of functions to another set of functions. And the big question is, how does the function phi determine the behavior of the operator? And that's the central question in the study of composition operators. Okay. Now, in this talk, I'm going to restrict myself to a particular growth condition. Okay. I'll assume that my functions are in the Hardy space. The Hardy space is, you think of it as a generalization of the LP spaces. Okay. If you've got function f of z, if it has this series expansion, Taylor series, expansion sum an z to the n. Suppose that's a holomorphic function in the unit disk. Okay, and we don't really care about other domains. The unit disk is good enough because everything else is conformally the same anyway. If this is a holomorphic function in the unit disk, then we say that this is in the Hardy space if the coefficients are square summable. So if the sum of
This index n ranges over the numbers or
n will range over natural numbers
okay, from 0 to
from 0 to if you include 0 in natural numbers. Okay. Yeah. So this is a particular example. It's just to illustrate really this what I'm going to talk about extends much further than this. So examples of Hardy space functions would be this. Okay, f of z is log of 1 and 1 minus z. So that's a function holomorphic in the unit disk, but obviously it's got a massive singularity at z is equal to 1. Okay, it's got a big one there, tends to infinity there. But it's not so badly behaved that it's not in the Hardy space. However, the second one there, f of z is 1 over 1 minus z, is too bad to be in the Hardy space. Okay, f of z is the sum of the an's there are all 1, so obviously that's not square sum of 1. So that Hardy space, the condition of being in the Hardy space is very much a growth condition on the boundary behaviour of these functions. It may not look like it, but in complex analysis there's a link between the coefficients of those Taylor series expansion and the growth of these functions. Okay. So they're not really nice, but they're fairly nice, these Hardy space functions. Okay. Alright, so where do we start with this? Well, we start with this what's called the Littlewood subordination theorem. Littlewood showed one of the most fundamental results really in this area is that if f is any function in the Hardy space, okay, and phi is any function, not necessarily conformal, any holomorphic function that maps the unit disk into itself, then f of phi is also in the Hardy space. Okay, that's massively important. That means that what it's saying is that phi can never be so bad that it kind of introduces new singularities or does something weird. It doesn't increase growth in any way. It always allows you to kind of keep things fairly stable. Okay. So this is the kind of central result really. This is where it all started with the study of composition operators. This was proved in the 1920s, you know, and that was as things like functional analysis were becoming really popular and as people really started to understand that differential equations and things are better understood with linearization. And so, you know, looking at operators and things, it wasn't necessarily the way this was discussed or proved. But eventually people realized that if you think about this in terms of operator theory, then what this is saying is C phi is a bounded operator. Okay, so this definition, f is in the H2, implies C phi f is in H2. That is exactly the same as saying that C phi is a bounded operator on H2. So what Littlewood's subordination theorem said was that no matter what phi is, C phi is always bounded. Okay, it's always bounded. Okay, bounded operators are also called continuous operators, by the way, if they're linear, so you might see that. Okay, so bounded operators are almost kind of done with, right? They're done with in terms of composition operators. Okay, everything is bounded for Hardy spaces. Compactness, on the other hand, is not. Okay, compactness turns out to be much more complicated. So, just to explain what a compact operator is, if a bounded operator maps this unit ball, okay, so think about the Hardy space, that space of functions, think about having the unit ball and where that is mapped from with your operator. Then a bounded operator is one where the unit ball is mapped to another bounded ball, basically. Okay, a bounded subset. But a compact operator is one where it maps that ball into a set with whose closure is compact. Okay. Think of compactness. You can think of a closed bounded set. Okay. This is a much more useful kind of thing, having a compact operator. The compact operators are much more interesting. They have very nice spectrums. They have a lot of theory that goes behind them. We can understand them a lot better. Bounded operators tend to be a lot more complicated. So compact operators are what I'll look at in particular, although the methods extend. With composition operators, you kind of want to understand what's the geometry of this domain phi, and how does it relate to whether or not your operator is bounded or compact. Okay, so remember, compactness is a stronger condition than boundedness. Okay, so if something's compact, then it is automatically bounded. Okay, so the top example there, you've got a mapping that maps the unit disk here into this ellipse. Okay, into this ellipse. That provides a composition operator that's bounded but isn't compact. Okay, whereas the second one provides a composition operator that is compact. Okay, so that is compact.
I don't get why the first one is compact and the other one is not compact. So compact means closed and rounded, basically.
No, the compact is a bit more than that.
The compact set is
Oh, sorry, yeah.
compact set is a closed and rounded.
The domains for the functions phi have nothing to do with the compactness of the operator.
Okay.
Well, I mean, the compactness of that set is nothing. Those sets will always be open sets.
Anyway, okay.
Okay? They will always be open sets. So if you look at these diagrams again, the one on the left provides a bounded operator, the one on the right provides a compact operator. And you might well look at it and think, well, there's not a great deal of difference there. Okay, they're both touching the boundary of the unit disk with at 1. Everywhere else is inside. But there is obviously a huge difference because they provide separate, very different composition operators. All right, so what is the real difference here? Well, the one on the right is obviously a polygon, but with polygons you get corners. Okay? Corners on a set where something like this is defined cause problems. Okay? They cause problems because you cannot extend phi to that point. Okay? You cannot extend phi to that point. If the domain of something like this is nicely defined, it's a nice little circle like that, then you can extend phi to that boundary. Okay. That's not quite true actually. You can still extend it. It's just you can't extend it to a differentiable function. Okay. Turns out that a composition operator is compact if and only if that boundary. Okay, the boundary of that domain is kind of differentiable. Okay, if you think of it as a smooth circle, if you can't differentiate something, it means there's some sort of crinkle there or some corner there. Okay, but only at the points where you've got where your domain is actually touching the unit circle. So it's not you don't care. You actually don't care about whatever goes on inside. You care about what's happening on the boundary. Okay, so it's only this point here at 1 that you care about. The fact that that is not differentiable there, that's the problem. Okay, and this all works really well. Okay, this all works really well. It's a nice little criteria. It's fairly easy to work out. There are definitions of the non-existence of the derivative that don't include anything about the derivative. They are purely geometric. Okay, so you don't even need to know about what's going on there. But the problem is, it's only true for simply connected domains. Okay, it's only true for simply connected domains. Phi is a function that maps the unit disk into a domain. Okay, if that is a conformal mapping into a simply connected domain, you've got a lot of nice stuff going on. Okay, it's 1-to-1 for a start. Yeah, actually that's pretty much it. That's all you care about. So there's this nice kind of correspondence, okay? One set is exactly the same as the other. One set is an exact copy of the other. Okay, they just change shape a little bit. Okay, so compactness on a simply connected domain, compactness where your function phi is a conformal mapping onto a simply connected domain is very well understood. Okay, very well understood. Turns out that it's also well understood for multiply connected domains. So a multiply connected domain is any domain where instead of just having a single boundary, you have a boundary with bits missing inside, or something like that, like points missing or something like that, or maybe a massive hole, but that one will count. I won't do anything here. But you know, multiply connected domains are any domain where the boundary is not a single bit. Okay. Okay, so it turns out that actually it's understood there as well, but it's a lot more complicated. Okay, it's a lot more complicated. The condition for compactness is much more difficult with multiply connected domain as this thing. Okay, C phi is compact if and only if this thing is true. Okay, I'm not going to read it out. This function n phi is called the Neven-Linne counting function. Okay, Rolf Neven-Linne invented this whole area, okay, to study metamorphic functions, and part of it was understanding, looking at this equation. So ignore the top one for a second. The important thing is what on earth this Neven-Linne counting function looks like. Okay, so remember, you know, phi is a function that maps the unit disk onto some set here. Okay, I've cleverly drawn a simply connected set. But imagine it's not simply connected. Okay? What the Neven-Linne counting function does is, for every point in the image, it counts, like does a kind of weighted count of the possible pre-images. So all of these points here are mapped to this point W. Okay? And what the Neven-Linne counting function does is it kind of does a weighted average of those. There's a weighted average. And it weights things, the log of 1 over z becomes, tends to 1, obviously, as z tends to 1, so that log tends to 0, okay, as z gets closer to 1. Okay, so it does this kind of weighting thing. Turns out these things converge, this very weird sum converges, and it actually it's fairly nicely bounded. Okay, but going back to the criteria, obviously it's quite difficult then to work with. Okay, there are about 3 cases where the Neven-Linne counting function is understood. Okay, one is in simply connected domains. Another is with a specific type of function called an inner function, and really that's it. Really, there are other examples, but the Neven-Linne counting function is quite hard to get to grips with. Nevertheless, we need to do it to understand compactness. Okay, to understand compactness. So simply connected domains are nice and easy. Their functions phi are 1 to 1. Okay, so phi to the minus 1, the inverse, the pre-images of those w's. There's only one of them. Okay, there's only one pre-image for every w. So actually, just knowing where that is enough. Okay. Now, I've got a couple of animations just to show you the complexity of multiply connected domains. In general, when you look at conformal mappings, you look at the image of a circle of radius r. So on the left, you've got a circle of radius r, and on the right, you've got the image of that under this conformal mapping. So this conformal mapping takes z to 1 minus z to the 0.3. Okay? And what it does is it maps that unit disk into this funny wedge-shaped domain. Okay? So this is an example of a conformal mapping. It's very nice, except at the point 1. Okay, except at 1.1. There you can't extend the function to a differentiable function. Okay? But everywhere else you can. Okay? Everywhere else you can. So this, if this was phi, C phi then would be a compact operator, yeah, compact operator. Okay, so this is what I'm talking about. C phi is a compact operator from here. Okay, now if you look at multiply connected domains, now this is the same thing except that I've mapped the disk conformally onto the disk without 0 in it. Okay, and again you see it starts fairly normally, but it soon gets really, really complicated, and eventually it starts cycling around. It's very difficult to understand way. Okay. Turns out that the pre-image for every single point in this image here, there are infinitely many pre-images. Okay? So this conformal mapping, you're mapping the disk onto the disk without 0 in it, right? Which is weird to start off with, right? Because you're mapping conformally a disk onto a simply connected domain onto a multiply connected domain. Okay? This is an example of how nightmarish boundary behavior can be. So obviously this kind of mapping does something very weird with the boundary, okay? Because at one point it starts moving parts of it inside. Okay, so this, but what you're doing is a conformal mapping is just a conformal mapping onto the disk without a single point. Okay, that's about as simple as a multiply connected domain can be, right? But this is I'm going to look at this example in depth, okay, to explain what's going on, because understanding this is the key to understanding everything with multiply connected domains.
Do you get similar or something like this, or similar weird behavior if you, here you're mapping something that is simply connected, as you said, to a domain that is not connected,
Yeah.
so it's missing a point. But if you would map something that is, so if you're
Already starting with missing
if you're already
points,
starting with something,
yeah.
Oh no, then that's a whole different thing, because you can map conformally a connected domain without a point onto any other domain without.
The identity, in
Yeah.
this case.
But yeah, because you just do the identity, or pick up suitable automorphism that moves that point somewhere.
okay.
You know, yeah. That's a whole separate thing. It's what you really want to know about is annulus. You know, how do you map an annulus onto another doubly connected domain? You know, that's an interesting question. Okay, because then there's not a clear way of doing that. Anyway,
It's still, when you think about this, it's still sort of thinking about it with the topology of real numbers, but the behaviour is something with a complex.
Yeah, and this
thing, right?
you know, at the start I was talking about the definition of holomorphic is entangled with this open set thing. You know, it has to be defined in the open set, and the open set is part of the definition. It's really important because the boundary behaviour can be, I mean, we're talking about the nicest functions in complex function theory. Okay, holomorphic, conformal mappings. Holomorphic functions are even worse. Okay, even worse. And boundary behaviour of those is a nightmare. Anyway, so multiply connected domains can be really weird. Okay, so I slightly abused notation here. You do see this in complex analysis a lot. It's very naughty, but phi to the minus 1 of W, we think of that as the set of all possible pre-images. Okay, so phi to the minus 1 of W consists of infinitely many points, and they all tend to the boundary of the inner disk. Okay, but in order to understand it, in order to kind of work out compactness, you have to at least have some sort of understanding of where these things are. Okay, but it turns out if you think about these things as a Riemann surface, then it turns out to be fairly, I won't say straightforward, but it's doable. Turns out that particular example has a very nice geometric configuration. Turns out the pre-images of any point